So 3.2, the title is differentiability. So students, differentiability implies continuity. Their graphs will be smooth and continuous, with a well-defined slope at, got frozen there, slope at each point. Some examples are polynomial functions, so polynomials, rational functions, trig functions, exponential functions, log functions. Okay, so these are just the few that will have nice and smooth turns. Now, differential means it has a derivative, which is the slope at point a comma f of a. So what we're saying is that if f has a derivative at x equals a, then f is continuous at x equals a. Now I just want you to bring up to your attention that the contrary, okay, the converse is not true. The converse is not true. So if I say if f is continuous at x equals a, then f has to have a derivative at x equals a. That is not necessarily true. Right, so scenarios where a function would not be differentiable at x equals a. The first one we are going to study is called a corner. So a corner, by definition, it's where one-sided derivatives are different, okay? Okay, here we go. I'm going to give us an example. We're going to start with the basic parent function only. As you can tell, this is going to be a V shape. And a V shape, we know the problem location is going to be at x equals to 0, okay? At x equals to 0. So let's talk about the one-sided derivative. We can start with the left side derivative. Limit as h is approaching 0 from the left, f of a plus h minus f of a all over h. Well, the limit as h is approaching 0 from the left, a is going to be 0, so 0 plus h is h. F of 0, guys, is just going to be 0. So I can take minus 0, but minus 0 is just going to be 0. So it's going to say f of h over h. Well, f of h is an absolute value of h over h. Now to take it out of this absolute value, we talked about this a lot in last unit, right? And the graph of y equals absolute value of h, okay, it's like this. H is here, y is here. So on the left side, this is going to be a y equals negative h. So we are going to take out a negative h over h. That reduces down to negative 1. So on the left side, and we kind of look at this and be like, okay, yeah, that's right. On that left side, the slope is negative 1. On the right side, we're going to use similar definition, except this time h is approaching positive. F of a, oops, I went too small there. Where did this go now? There you go. F of a, sorry, it's moving on me quite a bit here. There you go. F of a plus h minus f of a all over h. And again, a is going to be 0. So limit h approaching 0 from the right. 0 plus h is h. F of 0 is 0. So similar process. And again, we're back to absolute value of h over h. Because we are coming from side, so the right side is this piece on, there you go, this piece, right? So we're going to take y equals positive h. So equals positive h over h, which is going to be positive 1. Now, if we look at this, the limit exists, right? From the right side and the left side, except that they are different, meaning that they are not the same. So this is what we call a corner at x equals 0, because the slope from the right and left are not the same. Slopes are not the same at x equals to 0. All right, case number 2. So number 2, we are going to call this a cusp. Okay, so by definition is where the slopes of the secant line, the slopes of the secant lines approach infinity from one side and negative infinity from the other side, or vice versa. Okay, so i.e., we will start with something we kind of have seen before, f of x equals, and again, I'm just going to use the parent function, 2 over 3. So x to the power 2/3. So if we were to write this as a radical, index is 3, is x squared. So to graph this out, when x is 0, y is 0. When x is 1, y is 1. Okay, when x is 2, y is 8. Why am I saying 2? I'm sorry, when x is 2, y is not 8. My bad. Sorry. So when x is 2, 2 squared is 4, right? Cube root of 4 is a little bit more than 1. So it's going to go more like this. And because end of the radical, everything is square, y will always be positive. So it looks like a bird, okay? And again, guys, the location problem is going to be at x equals to 0, because I'm just going to work with the parent function. So similar process, we are going to do the left-hand derivative. The limit as h is approaching 0 from the left of f of a plus h minus f of a all over h. Well, since a equals 0, f of 0 is going to be 0. Okay? So this will tell us that f of 0 plus h is h minus 0 over h. So here's what we got. So the limit, h is approaching 0 from the left. I'm going to plug in h to the power 2/3 divided by h, okay? And the denominator, guys, is a power of 1. Okay, when you guys, and with the power of 1, we can write it to 5 over 5. So h to the 2/3 divided by h to 5 over 5. When we are dividing, we subtract. So the bottom has a power of 3 over, why am I saying 5 for? I'm sorry, 3 over 3. 3 over 3. h is 3 over 3. So when we subtract, I have on the bottom 1/3. Okay. Now, if I want to write it as radical, because some of us kind of work with radical a little bit better, okay? So h is approaching 0 from the left. So I'm going to pick -1/1000. And if we were to plug it in, 1 over cube root of 1 over, and remember this is a negative, okay? And it's okay to have a negative under cube root because I'm still going to be, okay, so cube root of a negative 1 over 1000. That's even smaller on the negative side. So we have 1 over small negative number. So this is going to give me a negative infinity. Okay, it gets bigger and bigger on the negative side. When we do the right-hand derivative, guys, it's very similar in terms of our definition. So limit as h is approaching 0 from the right, f of a plus h minus f of a all over h. Now the math is going to be exactly the same. All of this right here is going to be the same, reducing the same, this is going to be the same, okay? So when we plug it in, everything will get the same thing until we get to the end, okay? So basic algebra, all of it comes out to be the same. So now instead of picking -1 over 1000, I'm going to pick a positive 1 over 1000. So with this, when we take the cube root of a positive tiny number, we get a positive small number. And a 1 divided by a positive small number is going to be an infinity. So on the left side, we have a negative infinity. On the right side, we have positive infinity. So by the definition of a cusp, this is a cusp. Okay, one side has one infinity, the other side has another infinity, so therefore it's a cusp. So cusp at x equals to 0.